All right, here we go with our next example. We got a horizontal spring. It says that we stretch the spring with a force of 6 newtons, which causes it to stretch 0.3 meters. And then we stick a mass on the end and stretch it 0.4 meters, and it then goes in simple harmonic motion. All right, so the first thing it wants us to do is find the force constant of the spring. We can use the information that we were given at the beginning. We know that the spring force, the force being exerted by the spring, is equal to negative kx. So we can see in the drawing that the object has been displaced to the right, so we'll go ahead and put in 0.03 meters for that. We are looking for k, and then for the force, what force is the spring going to exert? Well, the spring is going to be pulling to the left, right? The force that we exerted is to the right, so the spring is going to pull back towards its equilibrium point to the left, and so we're going to go ahead and put in a negative 6 for the force there. Now, once we do that, we should be able to just take the 6, divide by 0.03, and we should get that k is equal to 200 newtons per meter. So we got the spring constant. All right. Now, the next question is, what are the maximum and minimum velocities attained by the vibrating object? Well, for letter B then, we should know that when it gets to the ends, it's going to have a velocity of 0. Now, that is the minimum speed. Now, if we're talking about the maximum minimum velocities, maybe we're including negative velocities as being the lowest minimum velocity. So we'll go ahead and look for that. Now, in order to do this, the easiest way is to consider energy, right? Because once the object is released, then all of the elastic potential energy will be turned into kinetic energy. So you could write out the conservation of energy equation. In the end, what we would end up with is that 1/2 kx squared, and this will be the initial elastic potential energy, should be equal to 1/2 mv squared, which will be the kinetic energy at the end. And so hopefully all of that energy is being transferred over. All right. Let me just show you, if you were to start with the work is equal to the change in kinetic plus the change in gravitational plus the change in elastic potential energy. Gravitational would go away. There's no work being done because we're looking at the spring object system. And so we'd end up with 0 equals k final minus k initial plus elastic final minus elastic potential initial. In the beginning, we have elastic potential energy, but in the end, we're doing the endpoint being right at equilibrium here. And so it would have 0 because it would be at its equilibrium point. Initially, when the object is stretched, it has 0 speed, but in the final, when we get to the equilibrium point, that's when it should be going its fastest. All right, and so therefore we end up with 0 equals k final minus elastic potential energy initial. We can move that over, and we end up with the equation that we stated right here. It's usually pretty easy when the work is 0, when there's no outside forces, no outside energy, and when we're only looking at 2 pieces of energy that are taking place here. So we can go ahead and work with that. We'll go ahead, we'll put in the 200 for k. The displacement there was 0.04, and that will be equal to 1/2 times the mass, which was 0.5, and then times the final velocity squared. Now hopefully you can multiply those out and get an answer of 0.64 equals that final velocity squared, and we square root it, and we get that the final velocity equals 0.8 meters per second. So that's the speed when we are at that equilibrium point. So that's definitely the max speed when it's moving to the right. When it's moving to the left, it would be negative 0.8 meters per second. So the minimum speed could either be when it's at rest at one of the ends or when it's going in that negative velocity direction. All right. Letter C asks for the maximum and minimum acceleration. All right. Now, in order to find the maximum minimum acceleration, there's a couple of different ways to do this, but I'm going to suggest that we just find the acceleration when it's out at its maximum point here, because we can solve for the force of the spring at that point. The force of the spring at that point would be equal to negative kx, because we already know what k is, 200, and we know what x is, 0.04. We should then be able to just multiply those, and we get 8. And so the force is equal to negative 8 newtons, of course, because it's in the opposite direction. Now, we know that F equals ma, so therefore, if the force is negative 8, the mass is 0.5, we should then be able to calculate the acceleration, which will be negative 16 meters per second squared. And negative just means it to the left, and that should make sense. If we pull the spring over to the right, then the acceleration should be towards the left. All right, sweet. Now we move on to letter D. Letter D says the velocity and acceleration when the object has moved halfway to the center from its initial position. So that's talking about this point right here. So halfway between 0 and that 0.04. We can do that. We can do that by doing basically the same thing that we did in letter B. However, this time our final position is going to be right here. So we're going to go ahead and we're going to change color here. So now we're looking at this point, which means that we're going to have both some elastic potential final and some kinetic final, right? If we start here and then we end at this point, we're going to have both of those. All right, so instead of just saying that the initial elastic is equal to the final kinetic, we're going to say that the initial elastic is equal to the final kinetic, which would be that 1/2 mv squared final, but it's also going to have that 1/2 kx squared, just like that final. All right, and so we can go ahead and put in the numbers. The numbers should be basically the same. Over on the left-hand side, we're going to have the 1/2 times the 200 times the 0.04 squared. Over on the right-hand side, we're still going to have that 1/2 times the mass, which was 0.5, times the velocity squared. And then we'll have the 1/2 times 200 times that x, which if it's halfway, it should be at 0.02 squared. And if you do the calculations there, you should end up with VF equals 0.69 meters per second, which is less than that 0.8 that we came up with earlier. Okay, lovely, lovely. We also, of course, want the acceleration at that point. And you could do this through using the trig equations or something else, but we're just going to go ahead and do the same thing we did before. We're going to find the force at that point. The force at that point would be negative kx, which will be negative 200 times 0.02, because we're halfway there. And if we do 200 times 0.02, then we get 4. So the force here is equal to negative 4 newtons. Which then we can go F equals ma. We put in the force, 4 for the force, and then we put 0.5 times the a, and we get negative 8 meters per second squared, which fits exactly what we expect it to. Remember that our definition of simple harmonic motion is that the force, or the acceleration, is proportional to the displacement from the center. And so therefore, if we half the distance, the acceleration should be half of what it was before. Sweet! Okay, moving on to letter E. This is our last question here. Letter E asks us for the kinetic energy, the potential energy, and the total energy in that halfway position. All right, so we can get all of those basically by doing what we did over here in letter D. So we'll do the elastic potential energy, which is going to be 1/2 times 200 times 0.02 squared, and we get a elastic potential energy, which is equal to 0.04 joules. And then we're going to do the kinetic energy, and the kinetic energy is going to be 1/2 times the mass, which was 0.5, and then times the velocity at that point, which was 0.69, and we're going to square that, and we should get a number like 0.1, it's 119, so I'm going to go ahead and round it to 0.212, sorry. And then we can add those together to get the total energy. So the total energy, mechanical energy at that point, is equal to 0.16 joules. Now, as a side note, if you were to calculate one of these energies back here in B, either that initial elastic potential energy or the maximum kinetic energy, either one of those will end up giving you 0.16 joules, which is good because we want our total mechanical energy to be conserved at that point. All right, well, that's in that for that question. Let's do one more.